Welcome. In this session, we'll talk about one more class of discrete time systems that are referred as causal and non-causal discrete time systems. Now, a discrete time system is said to be causal. So, a discrete time system is said to be causal if the output, let's suppose at any time n equal to n naught, if the output at any time n equal to n naught depends only on the input for n less or equal to n naught. Means if the output y of n at any time n naught is a function of the input values, means it is the function of the inputs, where n is less or equal to n naught, means n never becomes this greater than this n equal to n naught. So if this is true, then this system is said to be causal system. Now remember, the word causal has to do something with cause and effect. So this is very important property actually. This causal has to do something with this cause and effect thing. So in other words, for a system to act upon, there must be an actual cause. Means for a system to act on something, means to act on some value, there must be the value there. There must be the cause. There must be the cause for this system to act. In other words, a causal system does not anticipate the future values of the input. Means this, in other words, means the causal system does not anticipate the future values of the system. Means this causal system does not anticipate the future values of the input, but only responds to the actual present inputs. Means this does not anticipate the future values of input, but responds only to the responds only to the present value or present input. In other words, so this causal system means this is something that is derived from this cause and effect property. Means for a system to act upon, there must be the actual cause present there. So a causal system does not anticipate. In other words, this means simply the causal system does not anticipate the future values of the input, but only responds to the actual present input, means that is present there. As a result, we can sum up it like this. We can say if there are two inputs to a causal system that are identical, if there are two inputs, let's suppose there are two inputs to a causal system. So if there are two inputs to a causal system that are identical, if these two inputs are identical up to some instant of time. So up to some instant of time, if these inputs are identical up to some point of time. So if these two inputs are identical up to some instance of time, let's call that time m naught. Let's denote that time by m naught. The corresponding outputs must also be identical up to this same time. Means the corresponding output that will result from these two inputs that are applied to this causal system must be also same up to this instant of time. Means the outputs for these two inputs must be same up to this instant of time, up to this instant of time. Now let me repeat this whole property again. Now a system is said to be causal if the output at any instant of time depends only on the input values for n less or equal to n naught. So if the output at any instant of time, we say at any instant of, let's suppose n is equal to n naught, and this system is said to be causal if it depends upon the input values for n less or equal to n naught, means it depends upon the input values up to this instant of time only. Mathematically, we say the output at this instant of time is only a function of those values of the input which are which have only this instant of time, and is only up to this instant of time. Now this is very important property. This is causality is a very important property for a system. This actually comes from this cause and effect. This has something to do with this cause and effect property. In other words, for a system to act, means for a system to act upon any input, there must be a cause, means there must be that input present. In other words, this does not anticipate the future values of them, means if the input hasn't arrived yet, the system cannot respond to the input. Means if the input to the system hasn't arrived yet, then the system cannot respond to that input. If it is able to respond to that input, then that system is a non-causal system. Now, what does it mean? We can sum up this property by saying this. If we apply two inputs to a causal system that are identical up to some point of time, so that are same up to some instant of time, so the outputs for this system, means the outputs that will result for these two inputs must be same up to this instant of time. Now, if you see from the dictionary, the synonyms of this causality, are synonyms. I hope I'm getting it correct. Synonyms of this causality are physically realizable. If you see the definition, the definition is physically realizable system. So this is one synonym, and this is also sometimes called a non-anticipatory, means which does not anticipate the future values, non-anticipatory. So we say this is a non-anticipatory system. All right. Now let me give you some examples so that you may get an idea about what's the causal system. So, for example, if the system operates on x of n, and let's suppose the output is x of n minus 1. So this is the input-output relationship. Now this system output at instant n depends upon the past value of the system. It does not anticipate the future value. So this is a causal system. So this is the first example of a causal system. Same way you can say y of n is the output of a system whose input is x of n, is something like this: k running from minus infinity to n, x of k. So what is this system doing? It's simply adding all the values. This is adding all the values up to this instant n. So this is simply called a summer. In discrete time, this is referred as summer or accumulator. This is also referred as accumulator. This system is also referred as accumulator or summer, and this is also called a delay unit. So this system is a delay unit. So you can say this is again a causal system. In the same way, now examples of a non-causal system. Example of a non-causal system. If it anticipates the future values, for example, we can say y of n is the output of a system whose input is x of n, and this is equal to x of n plus x of n plus 1. See, the system output, meaning the system output y of n is dependent upon the present value of the input and the future value of the input. And the future value of the input means we must have x of n value there to do this operation, which is the addition operation. Meaning this system anticipates the future values that are in future of this input signal. So this is a non-causal system. Now, Can we have an example, practical example of this non-causal system? Yes, this causality is not an essential constraint in application is with the where the independent variable is not time. For example, in image processing, if we record this image, we can anticipate the future values. The computer can very easily anticipate the future values. So in image processing applications, you can have a non-causal image processing. Image processing applications, you can have this non-causal system. Similarly, in geophysical or meteorological, this branches of engineering. So geophysical or meteorological sciences, we can record the signal and later on this recall these. So these signals that are present in that we have in geophysical and meteorological branches of science, we can have this non-causal system. Means this causal, there is no restriction on this causality of this system on this system. So in these systems we can avoid this causality constraint, and this is very important. And this property, this causality property, is very important for systems. This is very important for that are actually physically realizable. This is very important. For example, in radar system theory, this is very important there. Same way, so in some of the applications, we can anticipate the future value where we have already recorded the signal. For example, in image processing, if we take the snapshot, we can later on recall, means we can recall the future values of the signal. Same way in this areas of science, we can recall the futures values of the signal, because we usually record the signals in advance and then we do the processing on the computer system or on these other systems. Then we can recall these, meaning we can anticipate the future values there. But for a system to be physically realizable, it must be causal. The system must be causal. What does it mean? The system input must be present, then only the system can operate on that input. Okay, this is very important. Now, two important classes of these systems that are related to this are referred as these causal and non-causal systems are referred as static and dynamic systems. Static is also referred as sometimes as memoryless systems, and dynamic system. Dynamic system. Static and dynamic systems. These are related to these this causal systems. Now, a system is said to be a memoryless system or static system if the output for each value of n is dependent only on the present value of the input. Means if the output at time n is only dependent upon the present value of the input, then that system is referred as memoryless system or static system. So the output will simply be a function of this present value of this input. So the output will be simply a function of this present value of the input. For example, this output is same as input. So this is one example of a static signal. In continuous time system, the example of this static or memoryless system is the resistor. For example, in resistor, output voltage you can say is equal to R multiplied by current. So the output voltage is dependent upon the present value of this current. So this has no memory, in other words. And this memory, means for a system to have memory, is something related to the storage. This is referred to something related to some kind of storage of the system. Means if the system has memory or storage, that system is a dynamic system. That system is a dynamic system. And if we talk about input-output relationships, means the system output will be a function of present, past, and it can be a function of future values of the signal also. So for a dynamic system, the system for a system to have memory or simply a dynamic system will be a function of this past and future values of this signal. For example, if you say the in continuous time, we have a very good example, that is the capacitor this voltage. Capacitor voltage is related to the capacitor charge or this current. We can say if V of t is I of tau, d tau, tau varies minus infinity to t. This is the voltage and current relationship. Let me write it. So this is I of tau, V of tau. So the output voltage of the capacitor is related to the current by this interrelationship, and this tells you simply that depends upon all the past values of this charge that is stored in the capacitor. In other words, this system has memory. This capacitor has memory. So this is a system that's called as a dynamic system. So same way, the system that a summer that I just showed above. For example, this is an example of a dynamic system. So this is a dynamic system. This is a summer. This is simply a summer. Same way, another example of this dynamic system is x of n plus x of n plus 1. This is again a dynamic system, although this is non-causal, but this is a dynamic system. This does not only depend upon the present value of this input, but also on the there's future value. So this must be stored there. So that's why this system has memory also. So this system has memory also, because this value must be stored. Only then this system can do this job. Otherwise, if this has not arrived yet, means if we haven't anticipated this value of the input, then how can we do this operation? So you can say this is a non-causal system, but it does require the memory. That's why this system is classified as dynamic system. So dynamic systems, in short, will have memory, and static systems are memoryless, meaning it's a function of only the present value of the input. I hope this definition is clear. So this comes from this causality property, this static and dynamic system. Now let's apply this causality property to the LTI system. Now let's assume the system is now LTI. So if the system is LTI system, if the system is an LTI system, what is the criteria for this system to be a causal system? What is the criteria for this system to be a causal? We know the output of a system whose input is x of n, whose input is x of n, is related to input by this convolution like this, and we know we can write it like this: k running from minus infinity to infinity, x of n minus k h of k. So this is the input-output relationship of an LTI system. Now, if we expand this summation, we can write it. Let me use this. From minus 2 values. So we say this is x of n plus 2 h of, I'm going to use from k equal to minus 2. So when k is equal to minus 2, this is minus 2 plus x of n plus 1. When k is minus 1, means when we substitute k equal to minus 1 in this summation, what will be this? X of n plus 1 h of minus, so minus 1 plus, put k equal to 0, this will be x of n h of 0 plus x of, put any k equal to 1, n minus 1, k equal to 1, x of n minus 2, h of 1, sorry, is not 2, this is 1, h of 1 plus 1. So if we expand this sum, we can write it like this. Well, what I have done here, I have started from k equal to minus 2. I have started the values from k equal to minus 2 and put k equal to minus 2. So this will be equal to x of n plus 2, h of minus 2, x of n plus 1, h of minus 1, When k is 0, this will be x of n, and this will be h of 0, and so on. Put k equal to 1, k equal to 2, and so on. Now have a look at this. We said the system is said to be causal if it does not depend upon the future value of this input. If the system does not depend upon the future value of this input, we say that system is a causal system. We say that system is a causal system. Now you can have a look. Why does the system depend upon the future value? This is the future value of the signal. This is the future value of the signal. This is the present time of this input. This is the previous value of the input. This is the previous value of the input. Now, as you can see, we don't have a control on the input of the system. We don't have the control on the input, but we have the control on the impulse response of the system. Means how we design the system, that's up to us. Means impulse response is up to us. Means the impulse response here is up to us, but we have no control on this. We have no control on the input of this signal. So what we can do to make this system only depend upon the present and past values of the input, means to make this system depend upon the present and the past values of the input, that will make this system a causal system. Then to do that, what we can do, we can make the impulse response to go equal to 0. So if we are able to make that change, means if we say impulse response is 0, these impulse response values are 0, then we say this system becomes a causal system. Now you can say that h of n, or simply h of k, should be equal to 0 when n is less than 0. From this you can check it. When n is less than 0, if the impulse response is 0, means what do you mean by n is less than 0? Means n is minus 1, n is minus 2, n is minus 3. So that will make it h of minus 1, h of minus 2, h of minus 3, and so on. If these values are 0, we say that system becomes a causal system, and the output of this system is simply given as this. So the output of the system is x of n, h of 0, x of n minus 1, h of 1, x of n minus 2, h of 2, and so on. So this is the output of the system if h of n is 0 when n is less than 0. H of n is 0 equal for this means simply when n is minus 1, minus 2, minus 3, h of this is 0. So this is the criteria. So this is the criteria for an LTI system to be a causal system. This is the criteria for LTI system to be a causal system, means h of n, or simply h of k here, is equal to 0 when n is less than 0. So this is the criteria for a system to be a causal system, for this LTI system to be a causal system. Please follow the examples from your book. In the next session, we'll do what do we mean by invertible systems. What do we mean by invertible systems? Let me end it here. Please follow the examples from your book. Let us end it here.